And in the case, also in the silicon carbide MOSFET, the advantage is the gate control and it's a fast switching. But the issue is always the arm is larger than expected, and that's because of low channel mobility. And this is mainly due to the higher interface density, which is 10 to 13 in the silicon carbide and SiO2 interface. And the trap is mainly due to the two reasons here. The residual carbon from the surface of the substrate prior to the oxidation, or carbon generated at the interface during the oxidation. The interface is always a huge challenge in silicon carbide MOSFET due to this additional carbon and residual carbon in the interface, and therefore the silicon carbide MOSFET always suffer with a high interface issues. Interface trap is shown here, so which the basic idea is very similar to silicon, but in the case of the SiC, we have very higher DIT. And usually the DIT, it can be the range up to more than 10 to 13 as shown here. And for comparison, in the case of the silicon, it's only in the range of the 10 to 10. And the most typical ways to reduce the DIT is to do the post-oxidation annealing. So you can see this is the data without the POA. But once without the POA, actually the DIT can be effectively reduced. However, the value is still in the range of 10 to 12. And therefore, more advanced process still needed to further reduce the interface state density. And one of the issues in the silicon carbide is how to accurate to estimate the DIT. And in the literature, they already report many different ways to measure the DIT. The high-low and then the conductance and substrate slope and charge pumping are very overused in the silicon-based technology. But in the silicon carbide, the C5S are very special one that can more accurate to estimate interface state density. So here is a literature report that the DIT value measured by the conventional high-low or measured by the C5S. So you can see the C5S can estimate the higher DIT, and which consider as a more accurate the interface state density in the silicon carbide interface. And also, under the on-state, the silicon carbide also suffers the BTI as well. So the BTI has been mentioned in silicon, has happened in the gallium nitride, but also happened in the silicon carbide. And this is a BTI measurement in the commercial device. So you can see that more than 6 volts can be observed in the commercial device under the positive bias or negative bias here. To understand the BTI in the silicon carbide can be very similar to the case in the silicon. In general, the interface charge cannot fully explain the BTI because you can see not only the interface charging, but also the near interface oxide trap or the box oxide trap can play the role in the end to lead to the BTI issues. So recently, there's a literature proposed the active energy region for the charge trapping, and the idea is very similar to the defect band mentioned in the gallium nitride. As long as you have the electron start to inject it, and then once you have the defect band, defect inside this dielectric, and then you can start to see there's a trapping here. This is the case with SiO2 on silicon, but also they can be the possible the SiO2 on silicon carbide and also have this defect band. As already mentioned in the gallium nitride in here, I won't review again, just a reminder that a similar concept is also employed in the gallium nitride to understand the BTI by using the defect band. So in the end, by using the defect band concept here, so this paper proposed very nice modeling as shown in the bottom graph with very correct modeling of the recovery. So the combination of both defect batch shows a good agreement with experiment data, especially for longer stress and recovery time. And finally, the important part for BTI is to have a lifetime prediction. So in this case, the empirical lifetime extrapolation by using the power law or thermal activation model. And therefore, you can see that the power law predicts an infinite increase of delta VTH. So increase can be large, while the later, this thermal activation model shows a saturation of VTH shift. But by using the defect band, the accurate lifetime extrapolation from this work reveals that overall there is a threshold voltage around 0.6 volt for VG 15 volt, and then the operating time for the 10 years. So that means that the different understanding of the BDI in the end can cause a huge difference for the lifetime prediction. And here is a report from the commercial product for the NBTI and PBTI in the warp speed Gen 3 1200 volt silicon carbide MOSFET. So clearly see that there is a BTI effect as well. And under the AC PBTI, because this is a stress and without stress, and therefore the VTH shift can be much smaller compared to the DC PBTI. In the case of a long-term offset stress, the HTRB is one of the critical consideration. The silicon carbide MOSFET lifetime under blocking condition might be characterized by the accelerated HTRB. That's usually we call as ALT HTRB. And silicon carbide MOSFET display relatively low leakage up to the average voltage. And devices are typically designed with some margin between the average voltage and the rated voltage of the device in order to ensure reliability and robustness for against high drain bias voltage, especially the over voltage transient. And this margin can enable accelerated drain bias testing above the rated voltage but less than the average voltage. So in this region, the oxide field in the JFET gap of the device can be high enough to induce a gate oxide wear out. So constant bias ALT HTRB testing shows that device display relatively low gate drain leakage until abrupt gate source failure occurs with little to no precursor signal, similar to what happened in the TDDB. So in this case, when we consider off-state reliability in silicon carbide MOSFET, this is typical breakdown voltage that's beyond like 1500 volt, and do the accelerated HTRB at this range, and then you can extrapolate the voltage around 800 volt when up to the 10 to 8 hours. But the issues usually for the HTRB in the DMOS, which will be the gate oxide in the JFET gate, can show the breakdown. So this is a SEM image of a fib cross section through the failure side of the warp speed silicon carbide MOSFET. And the arrows highlight the location of oxide breakdown that occurred during the accelerated life stress test. So here is another result from the commercial product related to the ALT HTRB. So you can see stress at a high voltage, but in the end want to understand that what would be the possible voltage you can sustain around more than 10 to 8 hours. And therefore, summary here is that in the case of warp speed planar MOSFET, under the ALT HTRB stress, the gate oxide breakdown is a main concern for the off-state reliability. And furthermore, to understand the ion stability is also the critical concern for the silicon carbide MOSFET. So in this work, there's a pulse, high voltage pulse, in order to understand ion stability in the silicon carbide MOSFET. But fortunately, you can see the ion stability is relatively good. There's only less than 3% shift here. So robust ion stability less than 3%, up to 1200 volt in all sample, are observed in the 25 and 175 Celsius degree. So this confirms that in this case, this sample with a very special silicon implantation on the surface does not introduce any stability issue on the high voltage pulse. And also, we can consider to use the novel circuit as we previously mentioned for the continuous switching to evaluate the switching stability in the silicon carbide MOSFET, which is under the hot switching and then the zero voltage switching testing. And we found out that this is ion stability during the continuous switching. And first, ion is stable under ZVS with respect to different temperature and switching frequency. So this is ZVS testing. There's no obvious ion degradation observed, but the ion is increased under the hot switching with respect to a different temperature and switching frequency. So you can see here with a high temperature, high frequency, under the hot switching, ion is increased. So more than 20% of ion increase under 200 kHz hot switching at a 175 Celsius degree, and more than 30% of ion increase at a 125 Celsius degree of the hot switching at the case of a 300 kHz are observed. So in this work, it's also showing that in the real application under the hot switching, the silicon carbide MOSFET can have a severe ion degradation. So finally, this is a reference for this lecture. Can be found, the part of the reference come from this book, and part of the reference come from the Professor Guido Kusenaken's his lecture slide in the IMAC and K-Leuven. And so part of the reference come from my lectures in the NYCU. And if you are interested in the full lecture courses for the one semester, you can refer to this YouTube link. Then you can find out the whole semester video recording.